Okay, now we have our 8.2 notes. 8.2 says graphing simple rational functions, or just graphing rational functions. And what we're doing here, rational. What is a rational number? Well, rational number, if you remember, we can write two numbers as the ratio of each other. So two numbers as the ratio, okay, of each other. So for example, we can have a over b, but b cannot equal 0. So we're talking about rational functions. It's going to have the form of f of x equals p of x over q of x. Okay, so now we're going in from simple functions to rational functions. We've talked about our inverse variation, which kind of leads us into this, and that we have the form of y equals a divided by x. We have an x in our denominator. Okay, that's kind of where we're progressing with this. And graphing, we've already been graphing in this 7.1 to 7.2, so we're kind of moving on from there. And the inverse variation function is actually a rational function. So the inverse variation of y equals a divided by x is a rational function. So let's graph it. Let's graph this inverse variation function when a equals 1, let's say. Okay, so let's graph y equals 1 over x. I want to see what that looks like. So the graph of this is actually something called a hyperbola. We haven't talked about these yet. We've talked about parabolas, but not hyperbolas. Please do not call it hyperbola. Hyperbola, okay? It consists of two symmetrical branches. So, you're going to have two symmetrical branches. And it's your domain and range are going to be all non-zero numbers. So basically every number except 0. And you'll see why in a second. So domain and range for this graph, the y equals 1 over x, your domain and range are going to be all non-zero numbers. Cannot equal 0, in other words. Okay, let's graph it. Let's see. Let's plug in some numbers. Now, why is it that it cannot be 0? Well, if it's 0, then you have an x or a 0 in your denominator, and you can never have that. So, x, y, negative 3, negative 2, negative 1, 1, 2, 3. I already know it can't be 0. It's going to be undefined there. So, 1 divided by negative 3 is negative 1/3, negative 1/2, negative 1, 1, 1/2, 1/3. Let's graph these. Okay, so negative 3, negative 1/3, negative 2, negative 1/2, negative 1, negative 1, and the, over here, 1, 1, 2, 1/2, 3, 1/3. And when you connect your points, your graph is going to look something like this. this is a hyperbola. You've got two symmetrical branches, and if you look, it's never going to equal x equals 0, and it's never going to have y equals 0. Okay? So those are your two rules here that we've got going on. Okay, so if it can't equal 0, our domain and our range, then we have vertical and horizontal asymptotes now. So we have a vertical asymptote, which different from when we were talking about our horizontal asymptotes in the last section, or in the last chapter. Vertical means it can't cross a vertical line. So vertical asymptote at x equals 0, and we have a horizontal asymptote at y equals 0. Okay? This is called your parent function for your simple rational functions. So this is the parent function of your simple rational functions. Okay? Okay, so we talked about the parent function of rational functions, which is just the y equals 1 over x. Let's look at some examples of rational functions and how we're going to graph these. So let's look at y equals 6 over x. And right away, two things you can do are to graph your asymptotes. Okay? Because you're in the parent function, you know that because it's in this form right here and has nothing extra added to it, next to it, so on and so forth, you know you're going to have a vertical asymptote at x equals 0, and a horizontal asymptote at y equals 0. And the way I show my horizontal and vertical asymptotes is by dashed lines. Again, it's just a common way to do it. And so we're going to have one asymptote here, and we're going to have another asymptote here. And this just shows you where your lines are not going to touch. And it's clear, and it's how they do it in other math levels as well. Okay, so let's plot the points to the left and to the right of the vertical asymptote. So let's choose some points. X and y, let's do -3, -2, -1, 1, 2, and 3. Again, I'm not using 0 because it can't equal 0. That would give me a 0 in my denominator. So looking at -3, 6 divided by -3 is -2. 6 divided by -2 is -3. 6 divided by -1 is -6. 6 divided by 1 is 6. 6 divided by 2 is 3. 6 divided by 3 is 2. Let's graph these points. So -3, 1, 2, 3. Up 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3. Okay, so at -3, -6, we have a point. I'm sorry, -3, -2. -2, -3. And -1, -6. There we go. So your graph is going to look something like this on this side. And again, remember, it's the same on both sides, so it should look similar. 1, 6, 2, 3, and 3, 2. And what have we done compared to our parent function? We've actually vertically stretched our graph, so to speak. We've moved it, made it wider, and it lies farther from your axes. Okay, and because it has the same asymptotes as your parent function, you also can say that your domain is the same. So your domain and range are going to be all real numbers. All real non-zero numbers. Remember, it can't equal 0. Okay, so that's how you graph one of these functions. Let's look at a little bit more of a complicated function now. Not so much complicated as just gets that we have a little bit more to do. So if you have a function in the form y equals a over x minus h plus k. Okay, how many of you remember your hk? Good, I hope you all remember it. X is going to be your h value, and y is your k. Okay, and these are where your asymptotes are. So this is your x asymptote, this is your y asymptote. You pull them out of here, okay? So, let's look at an example of this.